In this third video on the method of characteristics, we're going to look at the general case, which is the hardest case, where, unlike the previous cases, we have a right-hand side, and we also have some term that doesn't involve partial derivatives of u, so we just have u on its own. So just as we have done in the previous videos, let's jump straight in and have a look at a specific example of such a problem, and we're going to look at this problem here. So we've got the partial differential equation ux plus 3ui minus 5u is equal to 2x squared. So that's of the form that we saw just now. And we've got a boundary condition that says that when y is equal to 0, then u is going to be this quadratic equation in x. So 25x squared plus 10x plus 2. Okay, so this is linear, it's first order, it's inhomogeneous. So let's see what we can do with that. So as we've seen in the lectures, what we first have to do is define these characteristic curves. And the way that we do that is that we parameterize them by some parameter that we're going to call t. So in other words, we're going to write x and y as functions of t to define these characteristic curves. So we say that dx by dt is whatever the coefficient of the ux term is, so the partial derivative of u with respect to x. So in our case here, that coefficient is just the number 1. So dx by dt is equal to 1. And then similarly with dy by dt, we take whatever the coefficient is of the uy term, and we put that here. So that's 3 in this case. So dx by dt is 1, dy by dt is equal to 3. So those are very straightforward ODEs that we can solve, but we also want boundary conditions. So the way that we decide what those boundary conditions should be is to look at the boundary conditions for the main problem. And they're typically going to be defined along a line. So in this case, we've got boundary conditions for u when x is equal to some value x and y is equal to 0. So let's draw a little picture of this. Here are our axes, x and y. Now, our boundary conditions are defined just along this line when y is equal to 0, so in other words along the x-axis. And the way that we then choose the boundary conditions for the characteristic curves is to say that when the parameter t equals 0, so just to reiterate, we're thinking about x and y now as being parameterized by t for the characteristic curves. So when t is equal to 0, we should be somewhere along this line along which the boundary conditions for the main problem are defined. So in this case that means that our y-coordinate should always be 0, so y of 0 is 0, and our x-coordinate should be able to vary along this line, depending on some parameter that we're going to call s. So in this case, because our boundary condition is defined in this way along the line y equals 0, we fix y to be 0 and let x vary according to some parameter that we're calling s. So now we just have to solve these ODEs, and that's nice and straightforward because all we really have to do is be able to integrate constants. We need to be able to integrate 1 and we need to integrate 3. So if we integrate this pink equation with respect to t, we get that x is equal to t plus a constant, and then applying this boundary condition, that means that x must be equal to t plus s. And then if we look at this equation for y, again, integrate that with respect to t. On the left-hand side we get y, on the right-hand side we get 3t plus a constant, but that constant must be 0 because of this boundary condition here. So the ODEs have got solutions that x is equal to t plus s and y is equal to 3t. And we can rearrange this system so that instead of writing x and y in terms of s and t, we can do it the other way around. So we can write t and s in terms of x and y, and that's going to be useful later on. Okay, so we found the equations of these characteristic curves in xy space that are parameterized by the parameters t and s. So we've got the characteristic curves. But why is that a useful thing to have? Well, if we just have a look at what we've got so far, we started with this PDE, and we have now got the equations for these characteristic curves. And those curves are nice because along them the PDE reduces to an ODE. So along those characteristic curves the PDE becomes this expression here. So how have we arrived at that? Well, these two terms that involved the partial derivatives, so ux plus 3uy, along these curves you can write this as du by dt. So those terms that I've circled are just du by dt. And that's because if you use the chain rule, then du by dt is equal to du dx dx dt plus du dy dy dt. And we know that dx by dt along those curves is just, well, if we look up here and differentiate this with respect to t, we just get 1. So dx by dt is just 1. And then here, if we look at dy dt, then again, what is dy dt? Well, if we differentiate y with respect to t, that's just differentiating 3t with respect to t, and that just gives us 3. So du dt is equal to du dx plus 3 du dy. It's du dx plus 3 du by dy. So this is exactly the same. So we've replaced these partial derivatives with just an ordinary derivative. So this is now beginning to look like an ODE. What about the rest of the equation? Well, we've got minus 5u is equal to 2x squared. But because we've now got differentiation with respect to t, we should rewrite this in terms of s and t rather than x and y. So 2x squared in terms of s and t, well, we said that x up here was just equal to t plus s, so 2x squared is 2t plus s squared. So we've now got an ODE, du dt minus 5u is equal to 2t plus s squared. So the next step is going to be to see if we can try and solve that ODE. So the ODE that we want to solve is this one here. So du dt minus 5u is 2t plus s squared. So it's a first order ODE, and the method that we're going to use to solve that is going to be integrating factor. So we want to multiply both sides of this equation by e to the integral of whatever we've got in front of the u. So in this case we've got minus 5u, so it's going to be e to the minus 5t is going to be our integrating factor. So we multiply both sides of this equation by e to the minus 5t, and then we can recognise, as usual in these integrating factor cases, that the left-hand side of this equation is a perfect derivative. So it's d by dt of e to the minus 5t multiplied by u. And if you can't see why that is, just try doing it the other way around. So if you were differentiating this expression here, you'd use the product rule, and you'd get e to the minus 5t times du dt, which is here, times the derivative of this multiplied by this. So minus 5 e to the minus 5t times u. So this left-hand side is just this derivative. And then the right-hand side is like this. So I've multiplied this out here. So now we want to integrate both sides of this equation with respect to t. And if we do that, then on the left-hand side we'll have e to the minus 5tu, and on the right-hand side we'll have all of these integrals. And these are now integrals that we're going to have to compute. So we're going to have to compute the integral of t squared e to the minus 5t, the integral of t e to the minus 5t, and the integral of e to the minus 5t. Okay, so let's have a go at computing those integrals. So here they are, looking quite colourful. So we've got three integrals that we want to solve. This one in green seems to be perhaps the easiest one, because it's just the integral of an exponential. So this is just going to be minus a fifth e to the minus 5t plus some constant. And remember that we've really got two variables here, s and t. So whereas this would ordinarily just be a constant, this could be a constant that depends on s. So it's really a function of s. Then what about this blue guy here, the integral of t e to the minus 5t? Well, that looks like an integral that we can integrate by parts. So if we integrate by parts, we find that we have this expression here. Again, we've got some arbitrary constant that can depend on s, and if we then finish this integration by parts off, we get this expression here. So that's the blue integral. What about the yellow integral? So the integral of t squared e to the minus 5t. So again, that's a kind of parts integration type of problem. So if we just integrate this by parts, we arrive at this expression here. And then we recognise that this next integral is one that we've already seen before. So this blue integral here is exactly what we had up here, and so we can just substitute in the result, and we find that the integral of t squared e to the minus 5t is this expression here. So I'm not going to dwell on the details here, but it's just integration by parts. So if we now substitute in all of those integrals into this expression we've got here, then we find that we get, after a little bit of simplification and factorising, this expression here. Okay, so this is what e to the minus 5t times u is. But we want to find out what the function u is, so let's multiply both sides by e to the plus 5t. That means that on the left-hand side we'll just have u. That e to the 5t that we're multiplying by will cancel out this one here. And then we also have to multiply this c of s, which is a combination of those functions that we called c1, c2 and c3 that came from these integrals. We have to multiply that as well by e to the 5t. So this expression is, if you like, the general solution for u. However, that expression is in terms of t and s, whereas our original problem and our original boundary condition were in terms of x and y. So this is the point at which we now want to put everything back in terms of x and y. And we said earlier that t could be written as y over 3, s could be written as x minus y over 3. So if we substitute in here these expressions for s and t in terms of x and y, then we arrive, just by substitution and a little bit of simplification, at this expression here. So this is the general solution of the partial differential equation in terms of the original variables x and y. But we've still got some kind of arbitrariness here because we've got this function c that we don't know yet. And in order to determine what that function is, we're going to use the boundary condition that we were given right at the start of the problem. So we're going to apply the boundary condition that when y is equal to 0, u should be 25x squared plus 10x plus 2 in order to find that function c. So the way we do that is that wherever we see y in this general solution, we put 0, and that gives us minus 2 over 125, 25x squared plus 10x plus 2, plus c of x. This disappears because y is 0, and this exponential is just 1 because it's e to the 0. So we have this, and from our boundary condition, that should be equal to 25x squared plus 10x plus 2. So now if we just rearrange that to find c, so we move everything except c over to the right hand side, we get that c of x is equal to 127 over 125 times this quadratic expression. So now we're pretty much there. We found what the general solution is, and we found what this function c is. It's given by this expression that we just found. So now we just need to combine those two. So here's what we have. The expression for u, the expression for c. So we just need to replace c with that function. And that lets us arrive at the final answer. So we knew that c of x was this guy, so we actually want c of x minus y over 3. So wherever we see an x here in the expression for c, we should replace that with x minus y over 3, and that gives us this. So this is the final answer for this particular partial differential equation. Okay, so we've arrived at the final answer. It's quite a complicated looking expression for you, but we found it. Now we can check that this function is the correct answer. You could either do it by hand, but I've used a computer package called Mathematica. So if u solves the PDE, then if we substitute it back into the original PDE and look at u sub x plus 3u sub y minus 5u minus 2x squared, then we should get 0 if it is the solution. And if we ask the computer to do that computation, then we get exactly 0. So it definitely solves the PDE. Does it also satisfy the boundary condition? Well, again, we can ask the computer to simplify u of x and 0, and we find that it gives us 25x squared plus 10x plus 2, which is exactly what we wanted it to give us. That's the boundary condition that we saw right at the start. And then we can plot the solution. Now the black lines here aren't the characteristic curves like we saw in the previous example. They're just to demonstrate what the shape is of this surface. That's because in the previous cases, when we plotted the characteristic curves for the simpler problems, then the surface, or the function u, was constant along those characteristic curves. Whereas that's not true for this general case example, because along the characteristic curves here, rather than being constant, u satisfied some ordinary differential equation. So it's not quite so simple to visualise exactly where the characteristic curves are, because they're not just contours of this shape. But you can see that we have some nice solution here, x-axis along here, y-axis along here, and then u is just the height of this surface. And you can see that as y grows, then this surface gets quite big quite quickly, and that's because of this exponential term in y, so that grows very quickly as y increases. Okay, so that completes the problem. Hopefully the examples in the problem sheets and on past papers and so on will give you lots of practice for these kinds of questions. They can be quite fiddly in terms of the amount of algebra and calculus that you have to apply to them, but hopefully this demonstrates that the method of characteristics is quite a powerful method that lets you solve all of these first order linear partial differential equations.